A global warming mitigation primer. The overlooked climate solution. The oceans. Global warming is the difference between the radiative balance of the Earth prior to 1750, when we started intensively burning fossil fuels, and the current temperature average, which is about 61 degrees Fahrenheit or 16 Celsius. It is expressed as radiative forcing in watts per square meter, which is the number of extra watts of power that the Earth is receiving for each square meter of the Earth's surface, and it is about 1.6 watts per square meter. Carbon dioxide provides as much forcing as all of the other factors that contribute to positive and negative radiative forcing combined. The global surface is 510 million square kilometers, so about 816 terawatts of heat is currently absorbed at the surface, or about 45 times the world's average rate of energy consumption, which is currently 18 terawatts. Solar radiation isn't distributed evenly. The equator is hot and the poles cold, mainly due to the angle of incidence of the sun's rays as they reach the planet. The area lit by the sun's rays is greater at A, the equator, than elsewhere, B. So the solar energy falling on a unit area of the Earth's surface is greater at the tropics than at higher latitudes. Plus the fact that solar radiation is absorbed and scattered in the atmosphere. All things being equal, at higher latitudes the sun's path is longer and at the poles more radiation is reflected due to the albedo effect. Even in the tropics, the heat doesn't accumulate uniformly, as indicated in the following map of the primary areas conducive to ocean thermal energy conversion. The hottest areas in red in the vicinity of the Philippines and Papua New Guinea are also the prime areas of cyclonic action per the following. NASA estimates an average hurricane produces 1.5 centimeters per day, 0.6 inches per day of rain inside a circle of a radius of 665 kilometers, 360 nautical miles, and has the capacity to produce about 600 terawatts of energy, 200 times the worldwide electrical generating capacity. Plus the total kinetic energy of the wind produced by each storm is 1.5 terawatts. In 2010, NOAA's Joint Institute for Marine Atmospheric Research estimated the upper layers of the world's oceans is storing enough energy to power nearly 500 100-watt light bulbs for each of the roughly 6.7 billion people on the planet, or about 335 terawatts annually. A major tropical storm therefore moves about twice as much heat as is currently accumulating annually in the oceans due to global warming. The problem with tropical storms as a climate mitigating strategy is about 75% of the heat that produces the storm then moves towards the poles where it produces ice melt, which is contributing between 75 to 80% of the current measured sea level rise. Only about 25% of the heat of storms is mixed into the permanent thermocline, the layer of the ocean surface below the mixed layer, which can be between 25 and 200 meters. The significance of this heat movement was exemplified by the so-called global warming hiatus between 1998 and 2013, which was a period of relatively little change in global's average surface temperatures. The following figure from the Nature paper, Recent Intensification of Wind-Driven Circulation in the Pacific and the Ongoing Warming Hiatus by Matthew England et al., shows how a pronounced strengthening in the Pacific trade winds drove as much as 1.5 degrees of the surface heat each decade during this period to 300 meters in the vicinity of the Philippines. Stephen Ramsdorf of Potsdam University, in an article, What Ocean Heating Reveals About Global Warming, showed what happens to the thermocline when the trade winds subside. It thickens in the east and shrinks in the west. The heat that went into deeper water in the west during the periods like the hiatus simply sloshes back to the east, and warming returns with a vengeance, as has happened the past 3 years. To bring warming to a halt, we have to stop producing carbon dioxide emissions and move the accumulated heat of warming to a depth of 1,000 meters, where it takes at least 250 years for the heat to return. We protect the thermal integrity of our electronic and computing equipment with heat pipes. Why would we do anything less for the planet? The efficiency of a system using a heat pipe design to move the heat of warming into deep water is about 7.6%. It therefore produces about 25.5 terawatts of energy annually. Further, when this heat gets back to the surface in 250 years, it can be recycled to produce additional energy. This way, in about 3,250 years, the entire inventory of warming heat is converted to productive energy. The alternative, conventional OTEC, effectively pours cold water over the heat pipe rather than removing the heat out of harm's way. The current research in Nature, abysmal ocean overturning shaped by seafloor distribution, demonstrates the viability of the heat pipe approach. A large patch of ocean water about 6,000 kilometers by 2,000 kilometers between 1 and 2.5 kilometers deep in the Pacific and Indian Oceans has trapped ancient water for between 1,000 and 2,000 years. This stagnant water is devoid of oxygen and therefore much life. The movement of heat with heat pipes not only keeps warming heat away from the poles, it can produce, along with vital energy, convection that brings this area back to life. The convection can also enable recycling of the heat of global warming and therefore its ultimate and complete conversion to productive energy. Heat moved to deep water also produces half the sea level rise of heat at the surface, where the coefficient of expansion of seawater is higher. Instead of overlooking the ocean potential to solve climate change, we need to capitalize on this potential.